Hello everyone. Today we will discuss about Introduction to Proofs, section 1.7. A proof is a valid argument that establishes the truth of a mathematical statement. A proof can use hypotheses of the theorem, axiom, assumed to be true or previously proven theorems. Using these ingredients and rules of inference, the final step of the proof can be reached and established. In practice, the proofs of theorems designed for human consumption are always informal. Let's talk about types of proofs. There are two types of proofs. There are one, you have informal proofs, where more than one rule of inference may be used in each step, and some steps may be skipped. Sometimes axiom can be used as well as some rules of inference. Whereas in the formal proof, it is any proof that involves proposition and quantify statement to show that an argument is true. Construction of theorem statement. Many theorems assert that a property holds for all elements in a domain, such as the integers or the real numbers. When a theorem is proved, the first step of the proof usually involves selecting a general element of the domain. Then subsequent steps show that this element has the property in question. Methods of proving theorems. There are three methods of proofs. First, direct proofs. Second, proofs by contraposition. Number three, proofs by contradiction. Direct proof. To prove a statement for all x, where x is a member of the domain D, if P of x, then Q of x. So suppose x is a particular number which is arbitrarily chosen from a domain D for which P of x is true. Now we want to show that because P of x is true, we want to show also that Q of x is true. How do we do it? Well, we can use either something like definition that relate P of x and Q of x, or we can use an already established result that connect P of x and Q of x, or we can use rules of logic or rules of inference, quantify statement and so forth. This is how we use direct proof to establish an argument. So procedures of direct proof. The first thing is, if you want to use direct proof to prove a theorem, first thing is you write the theorem to be proved. Clearly mark the beginning of your proof with the word proof. Make your proof self-contained. Identify all variables used in the proof. State the source of outside facts. Write proofs in complete English sentence. Odd and even integers. Definition: an integer n is even if and only if there is an integer k such that n is equal to 2k. An integer n is odd if and only if there is an integer k such that n is equal to 2k plus 1. Proof by contraposition. Proof of theorems that are not a direct proof, that do not start with premises and end with conclusion, are called indirect proofs. There is a useful type of indirect proof which is known as a proof by contraposition. Proofs by contraposition make use of the fact that conditional statements such as if P then Q is equivalent to its contrapositive If negative q, then negative p. Example 1. Prove that if n is an integer and 3n plus 2 is odd, then n is odd. Now we will use direct proof. We first assume that 3n plus 2 is equal to 2k plus 1, where k here is some integer. 2k plus 1 comes from the definition of an odd number. Now subtract 1 from both sides, so I have 2k is equal to 3n plus 1, and from there I just came to a dead end. The the direct proof cannot prove to me that 3n plus 2 is an odd number. Now I will use proof by contraposition. So contraposition, as we know it, usually we use some sort of negation to prove a statement. So for instance, if 3n plus 2 is odd, then n is odd. We say this whole expression is false. That means n is even. All right. So if n is even, that means 3n plus 2 is also even. And then from definition of an even number, n is equal to 2k, unlike the definition of odd number, which says 2k plus 1. Okay, from there we substitute n is equal to 2k in the expression 3n plus 2, and then from there we found that 3n plus 2 is equal to 2 times 3k plus 1. That means, therefore, we conclude that 3n plus 2 is an even because it's a multiple of 2. Example 2. Show that the proposition p of 0 is true, where p of n is the following. It's the following statement. If n is greater than 1, then n squared is greater than n, and the domain consists of all integers. Note that p of 0 is if 0 is greater than 1, then 0 squared is greater than 0. We can show that p of 0 using the proof is true. Now the hypothesis is false, and the conclusion is false. Therefore, from the truth table, we can tell that p of 0 is automatically is true.
Prove that sum of two rational number is rational. Solution. We first attempt a direct proof. To begin, suppose that R and S are rational numbers, two rational numbers. So from the definition of rational number, it follows that a rational number is a number that we can express as P divided by Q, for instance. So we say R is equal to P divided by Q, and S is equal to T divided by U. So sum of both P divided by Q plus T divided by U, that give you PU plus QT divided by QU. Therefore, we have expressed R plus S as the ratio of two integers, which means that our attempt to find a direct proof have succeeded.
Prove by contradiction. Suppose the statement to be proved is false. Show that this supposition logically leads to a contradiction. Conclude that the statement to be proved is true.
Example 4. Prove that the square root of 2 is irrational by giving a proof by contradiction. Solution. Let P be the proposition square root of 2 is irrational. To start a proof by contradiction, we assume that negative P is true. Note that negative P is the statement. It is not the case that square root of 2 is irrational. Square root of 2 is irrational. There exists an integer a and b such that square root of 2 is equal to a plus over b and b not equal to 0. So if we square both sides of the equation, we get 2 is equal to square root of 2 divided by b. Hence, 2b squared is equal to a squared. And by definition, a squared is equal to b squared. That means 2b squared. That means a is even. So now let's assume that a is equal to 2c, and we substitute that back in the equation 2b squared plus a. And now we get that b squared is equal to 2c, where c here is an integer, which means that b is also even. We have shown that the assumption of negative p leads to the equation that the square root of 2 is equal to a over b, where both numbers have no common factors, which mean p, the statement square root is irrational, is true.
And these are the references we use to make this presentation.